Hello, this is Jishan Chowdhury from jsituition.net, and today we're going to be talking about stable and unstable nuclei. So let's start off by talking about stable atoms. So let's recall that the atom has a nucleus that's filled with protons and neutrons, and this nucleus is positively charged, and we have electrons that surround the nucleus. You should be familiar with this from GCSE. Now, like I said, the nucleus is positively charged, composed of protons and neutrons, and you might hear sometimes the protons or neutrons being referred to as nucleons to refer to particles inside the nucleus. And electrons are negatively charged, and as the nucleus is positively charged, the electrons are held towards the nucleus by an electrostatic force because there's an attraction towards opposite charges. So this table down here I've just put in just so we can consider the charges and masses of these individual particles. So things to sort of note of importance. So the electron has a much smaller mass than the proton. As you can see here, it's the power of the negative 31. So its mass relative to the proton is just much smaller. That being said, you might also notice the proton and the neutron have pretty much the same mass, almost equal. And the electron has an equal and opposite charge to the proton. The neutrons are pretty much uncharged. And a few definitions you might hear: an uncharged atom become an ion if it gains or loses an electron. And generally an uncharged atom has an equal number of protons and electrons. So we're now going to discuss isotopes. So each atom of any element has the same number of protons as any other atom in the element, and the proton number, also known as the atomic number, you might sometimes see as the symbol Z, represents this. So for instance, if we look at carbon here, it has a proton number of 6, so it contains 6 protons in its nucleus. We can look at nickel. It has a proton number of 28, so it has every nickel atom has 28 protons in its nucleus. Okay, the atoms of an element can have different number of neutrons, and we call these isotopes. So I've just written that there for you. Now, in the nucleus, we have the total number of protons and neutrons, which is given by our relative atomic mass, or sometimes called the mass number, or even the nucleon number, and that's sometimes denoted as just A. So generally, this is how we write isotopes. We have the chemical, so that, let's say X. At the top, we have the number of protons and neutrons, and at the bottom, we have the number of protons. So simply to work out the number of neutrons, then, if this is the number of protons and neutrons, this is just the number of protons, we just do A take away Z. Easy. So for instance, uranium, many isotopes, but uranium 238, let's say, has a chemical symbol as U238 as its atomic mass, and its proton number is 92. And each type of nucleus is called a nuclide, and we label it using this isotope charge. And specific charge of a charged particle is just simply defined as the charge of the particle divided by its mass. So as long as we know both these things, we can work out its specific charge. So for instance, the nucleus of a hydrogen atom has a charge of 1.6 times 10 to the minus 19 coulombs and has a mass of 1.67 times 10 to the negative 27 kg. So all you got to do is divide these together, and if you put that in your calculator, you get a specific charge of 9.58 times 10 to the 7, and the unit is coulombs per kilogram. How about an electron? Well, an electron has a charge of negatives. Remember, electrons have a negative charge, negative 1.6 times 10 to the negative 19 coulombs, and electrons have a mass of 9.11 times 10 to the negative 31 kg. So its specific charge is 1.76 times 10 to the 11 coulombs per kg. So electrons actually have the largest specific charge of any particle, and that's because they have a really small mass, so the overall fraction becomes really, really large. And let's say an ion of a magnesium isotope, and this actually has a charge of positive 3.2 times 10 to the 19. So 19 is positive because it's an ion, and it has a mass of 3.98 times 10 to the negative 26 kg. I'll let you guys work out the specific charge for that. So back to our nucleus. protons and neutrons in here. So protons are all sort of positively charged, right? So they must be having some electrostatic repulsion. So what's stopping everything just sort of spilling out and this whole atom just disintegrating? Well, there's a force called a strong nuclear force. So there'll be an electrostatic force wanting to cause this nucleus to just disintegrate. So what we figured out is there must be a force holding it together. And as I said, that is called the strong nuclear force. So a few things to know about a strong nuclear force. It's only about 3 to 4 femtometers in distance. Just to let you know how small a femtometer is, 1 femtometer is the same as 10 to the minus 15 meters. So extraordinarily small. So this is a very small force just pulling everything and keeping it back in. In comparison, the electrostatic force actually has an infinite distance, right? But I mean, obviously, the force decreases as we move away from the nucleus. But the actually in theory has an infinite distance or an infinite range. And this strong nuclear force, it doesn't just have the same effect between protons. It also has the same effect between a proton and a neutron, and even 2 neutrons for that matter. And as I was saying, it's an attractive force about 3 to 4 femtometers, and it can go all the way down to about half a femtometer. And after separation smaller than this, it actually becomes a repulsive force, which is interesting. And it actually prevents neutrons and protons being pushed into each other. This graphically, and distance from the center of the nucleus on the x-axis is 0 force, and forces above this line we call repel, and attractive forces beneath. So the electrostatic force, as we said, it tends to like to repel, especially when it's really close to the nucleus. But as we move further away, that force decreases. And the strong nuclear force does the opposite, where actually it wants to attract, but hasn't got a very large distance, so this attractive force does diminish as we move further away from the center and peaks about here. And we said it can go to about half a femtometer, and below this, so let's say this is half a femtometer here, it actually becomes a repulsive force instead. So naturally occurring radioactive isotopes tend to release 3 types of radiation. So start off with alpha radiation, which consists of an alpha particle, and an alpha particle has 2 protons and 2 neutrons, same as a helium nucleus. And we denote it like this. We say it's an alpha particle with a proton number of 2, and because it also has 2 neutrons, its atomic mass must be 4. Right? So let's think about what is actually happening. Looking at this figure here, what's actually happening when an unstable nucleus of an element emits an alpha particle? Well, its nucleon number must decrease by 4, because a nucleon or atomic mass number must decrease by 4, and its atomic mass or its proton number must decrease by 2. And then this just becomes a new element then, just called Y. So let's try and denote that. So let's say we had an element X with an atomic mass and a proton number. Well, after alpha decay, it will become a new element. We're going to call this Y, and this new element has an atomic mass that is 4 less than the element X. So we lost 4 particles, and because we've lost 2 protons, it must have a proton number of 2 less. And it's also emitted the alpha particle, so make sure we include that into our equation. There's also beta radiation, which is basically these fast-moving electrons, and the symbol for an electron, which is the beta particle, you can either write as 0, -1 beta, but sometimes you might also see it's written as just simply beta with a negative charge. Negative charge because it's an electron and it's got the equal and opposite charge of that of a proton. And it's also got a mass that is just much smaller than the proton's mass. So looking at this, let's see what's happening. So beta decay tends to happen when a neutron in the nucleus changes into a proton. And this tends to happen with nuclei that have too many neutrons. They just tend to spontaneously change into protons. When this happens, we have beta decay, and we also have an antiparticle, which we're not going to discuss in this video, but just know that an antiparticle known as an antineutrino is also emitted. Because the neutron changes into a proton inside the nucleus, the atomic number increases by 1. But of course, the total number of nucleons in the nucleus will just stay the same. So let's try and denote this. So we have particle X, atomic mass, and an atomic number, and it changes to a new element Y. Now it's still got the same atomic mass, nothing's changed there. because the neutron has changed into a proton, the proton number will increase by 1. We've emitted a beta particle, and we must remember with beta radiation, we've also emitted an antineutrino, which we denote by a V and a bar on top. There's also something known as gamma radiation, and gamma radiation happens when a nucleus has too much energy, and that's following after alpha and beta emission. So it's electromagnetic radiation that's emitted by an unstable nucleus with too much energy, and so it's released. It's an electromagnetic radiation emitted by an unstable nucleus which has too much energy. And for this video, all you need to know is it's very potent. It can pass through thick metal plates, unlike alpha and beta here. So that's sort of the basics of stable and unstable nuclei. You can go on our website, www.jctuition.net, for more physics tutorials and a further understanding of this topic. Alright, thanks for watching.